Hi there, it's Paul with a script designed to illustrate some properties of functions from R2 to R. In particular, the possibility of doing an affine approximation to a function, a constant plus a linear approximation near a certain point in the plane. And I'm also going to show you how to make visual representations of functions from R2 to R. In order to do this, I need to be able to calculate derivatives, so I have installed a package named numderiv, and the library function makes it accessible. I'm going to start off by reviewing the tangent line approximation for real-valued functions whose domain is just the real numbers. So, the function in question will be the sine function. And if I want to evaluate its derivative when x equals pi over 4, I use the function called grad. This is actually the gradient function in the special case where I'm working with n equals 1. And sure enough, I get the value 1 over the square root of 2, which is the correct value of the derivative. I can plot the sine function, and I can plot its first derivative as a function of x and get the cosine function. So we now have a way of calculating derivatives in R. I'm going to use this to illustrate the tangent line approximation. Here's a function, f of x equals sine of x to the 5/2 power. I can graph that function from 0 to 1 and pick a point at which I want to approximate it by the tangent line approximation, right smack in the middle at x0 equals 0.5. I've calculated the function value there, and to get the slope of the tangent line, I call the gradient function to evaluate the derivative there. And then the tangent line is a function of x which is equal to the value at x0 plus the derivative, the slope, times x minus x0. So this function gives the tangent line approximation, and if I plot it in red, you can see the beautiful tangent line. Although the graph of this function is a straight line, it is not a linear function. One way to see this is to note that f of 0 is not equal to 0. The correct name for this sort of function, a linear function plus a constant, is an affine function. Now, what's good about the tangent line approximation is that although it makes an error, the error goes to 0 faster than the amount by which x differs from the value x0. Let's just verify this quickly. If I look at the value of the function at x0 plus 0.2, that takes me up to 0.7, and subtract off the tangent line approximation, I make an error. I fall short by 0.048. If I do the same thing only 0.1 greater than x0, I still make an error, but the error hasn't decreased just by a factor of 2, it's decreased by a factor of 4, and this is typically the case. The error goes to 0 by an amount proportional to the square of the difference between x and x0. If I go only 0.02 away from 0.5, my original error should have decreased by a factor of about 100, and sure enough I get 2 more zeros in front of, well, it's 0.49 rather than 0.48, but still went down by about a factor of 100. Now let's try to do this in 2 dimensions. In order to look at this, we're going to have to know how to display a contour plot for a function. It took me several hours to figure out how to do this in R. I suggest that if you want to do this for your own functions, you copy my code and change the function. If you're really into computer science, you might want to look at the types or modes of the various quantities that are being created in R. But if you're not into computer science, just copy and edit. So here is a function f It's a function from R2 to R, and in fact it will work on any vector. But what it does is take the square root of the first component and multiply it by the log of 1 plus the second component. To check that it works, I create a vector whose components are 1.5 and 2.5. It calculates a function value. Now what I need to do is create a selection of points in the plane at which I'm going to evaluate this function. And I've decided to use x values that are spaced 0.1 apart from 1 to 3. Use y values that have the same range and the same spacing. So that means I'm going to have 21 squared pairs of values. And the way to make the pairs is to use a strange function in R called expand.grid. Give that 2 vectors, and it will create 1 row for every pair of values. Now what I do is to apply my function to each row. R has a function for doing this that's named apply. I'm applying it to pairs. The 1 as the second argument means I'm applying it row by row rather than column by column, and the f means the function that I'm applying is f. That will produce a vector. I don't want a vector though. I need a matrix of values, so I have to tell R that the number of rows in this matrix is the length of x. And I'm going to display the whole thing. So there down at the bottom you see the very end of the display. Those are the last of my 441 values, the values of the function for x and y at the upper end. If you like color, you can now call the function fill.contour. You've got to specify the x values, the y values, and z, the function values. And when you do that, you can see that lines where the function has a constant are the boundaries between colors. The pink values represent high function values. The blue-green values represent low function values. An alternative is to draw contour lines, and this shows us values where the function equals 0.8, 1, 1.2, 1.4, and so on. Now let's calculate the gradient of the function. I'll pick a point that's in my display. X naught equals 1.6, y naught equals 2.5, and I will call the gradient function on f evaluated at that particular point. And if you look in the lower left, you'll see I get a vector. That's the value of the 2 partial derivatives at that point. View this horizontally, it's the Jacobian matrix. View it vertically, it's the gradient vector. Now I can represent this by drawing an arrow. I draw an arrow from the point x naught, y naught to the point where I have incremented one by the first component of the gradient vector and the other by the second component of the gradient vector. And you can see that arrow showed up perpendicular to the contour line. That's showing that the gradient vector, which I displayed anchored at the point x naught, y naught, is perpendicular to the contour line along the direction of the greatest rate of increase. And by the way, this only worked because when I set up my original plot, I had an aspect ratio of 1 so that angles are represented faithfully. Now I'm going to use this gradient to do the best affine approximation to this function near my point x naught, y naught. Let's choose an increment vector I'm going to increment the x component by 0.4, the y component by 0.1. Let's choose a different x0, y0, 2.5, and 2. And now what I'm going to display is x0, y0, and arrows running to the incremented value of the vector. So this red arrow takes me from my original point of evaluation to my new point of evaluation displaced by the vector v. I can calculate the exact value at that new point by adding the two components of v to the two components of my point. There's the exact value of the function. But I can get a perfectly good approximation by computing the gradient, the vector with the two partial derivatives, and adding on to the value at the original point x0, y0, the dot product of the gradient and the vector v, or if you prefer, the matrix product of the one-row Jacobian matrix df and the column vector v. R does it the same way no matter what you choose. It multiplies the first components together, multiplies the second components together, and adds them up. There's my approximate value. It differs only in the third decimal place. The error in the approximation is quite small, and this approximation has the same property as was the case for functions from R to R. If I cut the increment in half by making a new increment vector that's equal to v over 2, and again calculate the exact value minus the approximate value, my error has gone down not by a factor of 2, but by a factor of 4. Now there is a way of doing the same calculation using nothing but single variable calculus. What I'm going to do is to define a function only on the line whose direction vector is my increment vector v. I will say, starting at x0, I add on t times the increment vector. When t equals 1, that's adding on the full increment vector, but this works for positive t, for negative t, or for 0t. It is a function of the single variable t. The way most people like to think of this is you are traveling along a straight line through the point x0, y0, whose direction vector is the vector v, and you pass through the point x0, y0 at time t equals 0. If I take the gradient of this function evaluated for t equals 0, I get exactly the same gradient vector that I had before, multiplied by the vector v. In other words, the derivative of this function with respect to t, which is the definition of the directional derivative, is equal to the dot product of the gradient vector df and v. And it will turn out, when we finally learn the definition of differentiability, that this property is the definition of differentiability. If the gradient vector calculates the correct directional derivative for every v, then the function's differentiable at the point. Let's finish up by looking at the gradient as a vector field. The function g that I've chosen to define is actually one that's quite important in physics, and when those of you in physics study electric and magnetic dipoles, you are likely to encounter this function. Notice that if I plug in the vector 0, 0, I get 0 over 0, and this function is going to behave rather badly near the origin. On the other hand, I can evaluate it far away from the origin, and it gives me a perfectly good function value. So as before, I choose a sequence of values for x. I choose the same sequence of values for y. I make my table of pairs of values, use the apply function in order to make a matrix of function values, and then display a whole bunch of contour lines for this function. And you can see, for example, that we get a circle off to the right where the function value is 1, a circle off to the left where the function value is -1. And now I'm going to plot lots of gradient vectors on this graph. In order to get the length reasonable, I need a scaling factor. 0.03 worked nicely for me. There's some x values conveniently excluding 0, some y values conveniently excluding 0. Here is the evaluation of the gradient vector at each point x, y. And now I'm going to draw arrows that represent the gradient vector, but in each case the arrows are going to be vectors anchored at the point x, y. Let's see what it looks like. And you can see those beautiful red arrows always pointing perpendicular to the contour lines along the greatest rate of increase of the function. To finish up, I want to show you what happens if we plot some pathological functions that don't have a limit at the origin. My first one is going to be product of the two components over sum of the squares, xy over x squared plus y squared, if you like. I have carefully defined this function to equal 0 at the origin, just so that r won't get upset if it's asked to plot the function there. So now I can safely choose my usual sequence, going from -1 to 1 in x, from -1 to 1 in y, use expand grid to create 441 pairs of values, apply the function f to make a matrix of function values, and now call the function contour to show the contour lines. And in this case, it becomes very clear what's happening. The function value is constant along every straight line going through the origin, and it depends only on the slope of that line. That makes it very clear that no limit can exist at 0, because all values from -1 to 1 are represented inside any arbitrarily small disk centered on the origin. If you prefer, you can show this with color. The function value is negative where the color is cyan. The function value is positive where the value is pink. Here is a sinister function invented by the Hubbards, which is discussed in the lecture notes. It involves exponentials and all sorts of yucky junk. The interesting thing about this function is that while it has a limit of 0 if I approach the origin along any straight line, it does not do that if I approach along a parabola. So I've tried plotting this using exactly the same code, making my matrix of values, showing the contour lines, and the peculiar feature of this function is that along the parabola y equals x squared, it has the constant value 1 over e, and you can see those 0.35 contour lines. On the other hand, r doesn't seem to be able to figure out how close they get to the origin. I can fix that. What I will do is to use sequences that range only from -1 to 1 for x, and from -0.01 to 0.01 for y, because it's on the parabola y equals x squared that interesting things happen. I do exactly the same thing, and the plot looks almost exactly the same. And that, in fact, is characteristic of lots of these pathological functions. They're self-similar. If you zero in on the point of interest, things do not get nice and smooth and simple. In fact, things look much the same.